Imagine a vault that keeps your most valuable data safe, but there's no handle on the door. You can put information in, it stays protected, but you can't reliably get it back out. That's been the paradox with one of the most promising kinds of quantum bits, Majorana qubits. Ultra-stable in theory, practically unreadable in the lab. That changed in February 2026. A joint team from Spain's National Research Council, CSIC, and Delft University of Technology figured out how to read Majorana qubits cleanly in real time. They built a tiny Lego-like device and used a clever electrical probe to tell which state the qubit was in, and they watched that state stay coherent for more than a millisecond. If you don't live inside a dilution refrigerator, here's why that's a big deal. Today's leading quantum machines fight constant noise. Engineers babysit them, calibrate, measure, correct, repeat. Majorana qubits take a different path. They're designed so the information lives in a non-local way, spread out, so local noise has a harder time scrambling it. The dream has always been fewer errors, less overhead, more scalable systems. The catch is, until now, we didn't have a reliable way to read the state without ruining the protection. The safe was great. The handle didn't exist. So let's slow that down for a second. What exactly happened and why should you care? In mid-February 2026, researchers at CSIC and Delft announced the first successful readout of Majorana qubits using a technique called quantum capacitance. They didn't just read a statistical blur, they could discriminate in a single shot between the two key states, what physicists call even and odd parity. And they watched something crucial. The parity stayed stable for longer than a millisecond before randomly flipping. In other words, they made the once invisible 1 and 0 of a Majorana qubit visible, and they stayed visible long enough to matter for computation. Here's the thing. Majorana qubits don't store info in a single spot. Instead, they use two linked quantum states, Majorana 0 modes, sitting at two ends of a tiny structure. Imagine splitting a password into two halves and locking each half in a different safe on opposite sides of the room. A thief who jostles one safe learns nothing. That's the topological protection people talk about. The information is non-local, so local noise has a hard time getting to it. Beautiful idea, brutal to measure. Traditional quantum measurements poke at one spot, one safe, and that's like asking half a password to confess. You just don't learn the whole story. The team's insight was to stop poking locally and instead sense the whole system at once. That's where the quantum capacitance trick comes in. Capacitance is a measure of how a system stores charge when you nudge it with a small voltage. Quantum capacitance is the subtle quantum part of that response. If you set up the device right, that response changes depending on the overall parity, whether the system is in the even or odd state. You're not counting individual electrons at a specific site, you're feeling the global state. Think of it like standing on a seesaw blindfolded. You can't see which side has a person, but you can feel the tilt under your feet and know the overall balance. That tilt is the quantum capacitance signal. Now, how did they build a device that hosts these Majorana modes in a controlled way? They went with what's called a Kitaev minimal chain. Don't worry about the name. Picture two semiconductor quantum dots, tiny islands that can hold electrons, connected by a superconductor. It's a compact bottom-up assembly, assembled with precision, more like snapping Lego bricks together than carving something out of a giant crystal. This Lego approach matters because it gives you knobs, voltages, couplings you can dial to reliably create and control the Majorana modes at the ends. So, two dots, a superconductor bridge, carefully tuned. You get a pair of Majorana 0 modes at the ends. That pair encodes a qubit in its even or odd parity. Then, instead of asking one dot what it sees, you use a global, non-invasive probe, quantum capacitance, to feel the whole system's parity. And it works. Here's what actually matters here. They could tell the state in a single measurement, and the state stayed coherent for more than a millisecond. In today's quantum hardware, a millisecond can feel like an eternity. That's time you can use to perform gates, move information, and correct the occasional error. Let that sink in for a second. They also saw random parity jumps, roughly once per millisecond on average. That sounds scary, but it's actually useful.
Those jumps are fingerprints of the remaining noise. Knowing how often and why they happen gives engineers a direct target for improving materials, shielding, and air handling strategies. If you followed this field, you might remember Microsoft's Majorana 1 announcement back in 2025. That was a separate step, a chip architecture and material system aimed at topological qubits, important momentum but not the same as this. The CSIC Delft work focuses on readout in a minimal, controlled device. It's the "can we read the qubit reliably" question, now with a clear yes. Let's take a breath and sum up the core idea so far. Majorana qubits promise stability by storing information non-locally. The challenge was reading that information without breaking the protection. By building a precise 2-dot plus superconductor device and using quantum capacitance as a global probe, they read the parity in real time and saw it stay coherent for over a millisecond. That's the unlock. Why does this shift the path to practical quantum computers? First, it validates the protection principle in hardware you can engineer. We're not just hoping the math works, we're seeing the signal. That builds confidence to invest in scaling. Second, topological qubits, if they continue to show long coherence, could need far fewer helper qubits for error correction. Today's leading approaches often need many physical qubits to make one logical, reliable qubit. Even a modest reduction there changes the economics of building machines with millions of effective qubits. Third, the readout method itself, sensing a global property instead of poking locally, fits well with scalable control. It hints at measurement and control schemes that could be less finicky than the status quo. And finally, it gives the field a benchmark, millisecond parity coherence with a clean readout. Hardware teams now have a number to beat, a device recipe to refine, and a readout to replicate. So let's slow that down one more time. The key thing here is the combination, not just one ingredient. Bottom-up device design for controllable Majorana modes, a global readout that sees parity directly, and measured stability that's long enough to plan around. That trio moves this from interesting physics to engineering blueprint. If you're wondering how this shows up outside the lab, think about 3 domains. In quantum hardware, this points towards simpler scaling stories. If each qubit is more stable on its own, you spend less of your system on firefighting errors. That means more of your system can do actual computation, chemistry simulations, optimization, materials discovery.
In AI-adjacent workloads, specialized quantum routines could complement classical accelerators. No one's throwing away GPUs, but a stable, gate-capable quantum coprocessor that reliably runs certain algorithms could change the shape of hybrid systems in finance, logistics, or drug design. And in cybersecurity, steady progress like this tightens the timeline pressure. Even if cryptographically relevant quantum computers aren't here tomorrow, the prudent move is to migrate to post-quantum cryptography on a schedule, not in a panic. Now, it's worth being clear about what's not solved yet. This demo is a minimal chain, a single qubit environment. Scaling to many qubits, routing them together, and performing high-fidelity gates are still open. There's also the iconic braiding operation, exchanging Majorana modes to fully demonstrate the topological logic people envision. That's on the roadmap, not in the bag. Those parity jumps, they're informative, but they're still errors. Reducing their rate, understanding their sources, quasi-particles, material defects, residual coupling, will take careful work. And the field has had false starts. Past Majorana claims have faced debates. The difference here is the clarity of the readout and the controlled device design. But skepticism in science is healthy. Independent replication will matter. If you're exploring this space, here are a few practical takeaways. For hardware teams, the combination of a bottom-up Kitaev-style chain and quantum capacitance readout looks like a reproducible template. Watching how quickly other labs replicate the millisecond parity coherence will tell you how robust this recipe is. For tech leaders and product folks, when you evaluate quantum roadmaps, ask about readout pathways and coherence under measurement. It's not just how long is T1 or T2, it's how stable is parity when you actually measure it, and how clean is the single-shot discrimination. For security leaders, this is another nudge to keep post-quantum migration on track. Inventory your cryptography, prioritize high-value systems, and adopt the new standards as they stabilize. The goal is a smooth transition, not a scramble.
For data and AI teams, keep an eye on early hybrid demos, classical plus quantum workflows where a few stable qubits can shift a bottleneck. You don't need 1,000 perfect qubits to see targeted wins, but you do need reliability. This work points in that direction. For anyone budgeting or investing, the signal to watch is not just glossy announcements. Look for peer-reviewed results with clear, single-shot parity readout, rising parity lifetimes, and error rates trending down under realistic operating conditions. So where does this go next? Near term, expect larger chains, adding more dots and junctions to test how coherence scales. The community will push toward implementing gates on these protected states, with 2027 often mentioned as a reasonable horizon for more complex operations if progress holds. On the system side, look for integration work, bringing this readout into cryogenic control electronics or coupling it with microwave resonators for multiplexed measurement. If you see clean, simultaneous readout of several topological qubits with millisecond scale stability, that's a strong signal. And in industry, you might see pilot efforts where topological qubits live alongside more conventional qubits, each used for what it does best. It's less about a single winner and more about assembling a stack that's reliable end to end. Let's revisit the heart of it one last time. Majorana qubits promised a kind of built-in armor against noise by encoding information non-locally. The missing piece was reading the state without poking holes in that armor. By building a precise, minimal device and sensing its global quantum capacitance, researchers finally got a clean handle on the state, and it held steady for over a millisecond. In other words, the safe finally has a handle, not a flimsy one, a practical one. And when that happens, everything downstream, gates, scaling, architecture, starts to look less like speculation and more like engineering. A few things to keep in mind as you watch this unfold. Replication is the next milestone. If multiple labs report the same single-shot parity readout and similar coherence, the confidence jump is real. Stability under load matters. It's one thing to keep parity coherent at rest. It's another to maintain it while performing gates. That's the next test. Tooling and manufacturability will separate demos from products. The Lego-like bottom-up build is promising here because it's modular. Modularity is friendly to automation. It's rare in quantum computing to see a long-standing conceptual promise click into an experimental method this cleanly. It doesn't solve everything, but it solves the piece that tells you the qubit is real, readable, and resilient enough to plan around. That's the kind of shift that changes conversations in boardrooms and lab benches alike, from if to how. So why does this matter? Because it turns a decade of almost into a blueprint you can build on. Because it suggests a path to qubits that don't spend their lives fighting the room. And because it reframes practical timelines, not to tomorrow, but to something you can plot on a roadmap without crossing your fingers. That's the story for now. If you found this useful, a like and subscribe helps us keep making these videos. Thanks for watching.